speaker is Dr. Mikaela. She's a physical scientist at the USGS Central Plants Water Science Center, and she'll be presenting two talks actually today. One on behalf of her colleague, Dr. Hobza, who's not able to make it to the conference today. That, Mikaela.
Hi, everyone. Like Dr. Malakar said, this is going to be, instead of two separate presentations, one giant presentation, so you get to hear me for extra long because Chris couldn't make it today. But both of these kind of projects deal with nutrient management strategies and how they impact groundwater. And so the first kind of project, we call it the Soil Nitrate Project. It's with the Lower Loop Natural Resources District. If you're not from Nebraska and haven't heard about NRDs and some of the other talks, these are just the state's broken up into 23 NRDs, and they're in charge of kind of managing their district, right, in terms of natural resources, groundwater quality being part of that. And so this project was to look at the effect of different fertilizer applications on potential groundwater contamination. And then the second project, which we call our Legacy Nitrate Project, is with Lower Loop and Lower Platte North NRDs. And that's to look at groundwater age dating and how that relates to the effectiveness, again, of nutrient management strategies. So kind of how both of these projects came into being, there were some comments made a couple of years ago about the groundwater nitrate problem is a legacy problem. It's not due to current management strategies. It's, like 40, 50 years old. At the same time, Lower Loop NRD was beginning discussions to ban fall fertilizer applications, so like fall anhydrous. That got a lot of pushback, like a lot of pushback. And so in January of 2023, they had, a bunch of public meetings. There was a lot of outrage about it. And so the board decided, okay, we're going to implement a few other strategies, and we'll come back to this idea of banning fall fertilizer. So after that meeting, the NRD started working with us, and they're like, hey, we need a study, we need to come up with something to back up, these recommendations or these bans that we're proposing. So we started developing a study plan to look at soil nitrogen throughout the growing season, throughout the vadose. And kind of at that same time, we had received a grant to work with the two NRDs to look at the legacy nitrate, and so we did all of our data collection for that. And then since then, the soil nitrate project, so we had the 1 year of data, the 2024 growing season. We're now just starting to finish up the 2025 growing season, and then next year we're expanding to a couple other NRDs to continue that project as well. So where we are in this state, the Lower Loop NRD is the purple NRD on the left, and the Lower Platte North NRD is the one on the right. And so we're kind of, in the eastern section of one and the western section of the other. The study areas kind of overlap. For the legacy nitrate, we kind of run along the Loop River as it goes into the Platte towards Fremont, that whole river valley area. And then the soil nitrate is a little bit, just a tiny bit northwest of that. And so for the soil nitrate, oh, it clicked, okay. So the board reached out to a lot of those producers that came to them and were like, hey, we don't like what you're implementing. And they're like, all right, you want to be part of this study? Kind of being prove that your management strategies aren't impacting anything. And so we ended up getting 10 different producers for 10 fields with a variety of fertilizer practices. So the fall anhydrous applications, the type that the ban was proposing, manure, and that could be either fall or spring or both applications. And then side dresses, we consider anything that's happening in season. So it didn't really matter how you were doing it in season, just in season. And you can see the different spread of, the different producers and their fertilizer practices. All of our sites are the Nora Crofton Moody Soil Association. That was not intentional. We got the producers first and started looking at where they were later, and just so happened they were all the same soil type, really handy. These are deep, well-drained upland soils. They're silt loam or silty clay loam. They tend to have moderately high to high infiltration, and this whole area in general tends to be irrigated corn and soybeans where there's groundwater, all of these sites have center pivot irrigations, and all but one had a flow meter to track irrigation throughout the season. And so how we approached this is we collected soil cores, and by we, I mean the NRDs did all of this work, collected soil cores at these 10 fields at specific crop stages. So instead of targeting, like we're sampling everything May 15th, they're like, the NRDs drove all the fields every single week, and they're like, all right, this field hit V6, we're sampling it now. And, so if there were delays in planting or things like that, all the fields are sampled same growing stage instead of same date. 30-foot samples were collected as like the pre and post seasons, like when the crops weren't on the field. And then in-season collections were 8-foot samples. The cores, were subdivided, bagged up, and we sent them to Ward Labs. For those of you outside of Nebraska, Ward Labs is located in Kearney. They do a lot of both water and soil sampling or analysis for producers and NRDs in the state. And one of the reasons we wanted to use Ward Labs as opposed to like a USGS or a national lab is because producers use this lab as well. It's someone they trust, it's someone they know. And so like they know where that data is coming from. So I talked about kind of like the corn stages, and so much of the nitrogen use for corn is happening V6, so like the first 6 leaves, to V18, which is like full tassel height. Someone correct me if I'm wrong. And that tends to happen like mid-June to mid-July, so like pretty early like in that corn development. And so if you're doing fall anhydrous, that's generally applied mid-November, early December, depending on weather. And then that's sitting on the field until potentially mid-June. So that's a long time of that fertilizer sitting on the field, hopefully doing nothing, but maybe not. In addition to all of our soil samples, we also had soil moisture probes at 3 of our sites and a precipitation gauge at all of those sites as well, to look at kind of just like how the soil moisture is changing throughout the year, identifying those irrigation events or precipitation events. And not intentionally, but we kind of learned we could track the movement of root growth through the season via those soil moisture probes. And we also did a bromide tracer test just to kind of get an idea of how quickly is water and therefore nitrate moving through the system. And so just to give me an idea of 2024 had at least for the area that we were, had a wetter early summer and a drier and like much drier or late summer, early fall. So more water in the beginning of the growing season and not a lot near the end. And so we applied bromide in June and then sampled it in August. So it wasn't on for like a very long time, but we definitely saw a lot of movement of it in that time. And so here is an example of one of our soil moisture plots. It's kind of a busy graph, and so I apologize if you can't see it in the back, but just like going with depth and then just the soil moisture. And you can see like in the upper few inches, you can see a lot more movement based on irrigation, precipitation, things like that. And as you get further down, you kind of reach like a field capacity level. And you can see at the 15.75 inches, like it's at field capacity until like midsummer, and then you can kind of see the roots start to get into that zone, and you see a bit more movement of, like it's not just like steady state. So and so I guess I should have related that back. Once we get like kind of past that 15, 16, we're going to call it 2 feet zone because it makes it easier for the data that we have. We're going to call the active root zone anything 2 feet and shallower, which I know goes against a lot of what we are taught for corn depth and corn root growth. But we also looked at we did an analysis like post-harvest at that root bulb and looking at like where is the corn taking up the water and the nitrogen in that root zone, and it really was in that top 2 feet, so it was shallower than we thought. And so in that top 2 feet, there's a lot of stuff happening. So we have these measurements from our soil, but like there's fertilizer being applied, there's things volatilizing, the plant is uptaking, some of it's moving down. It can be really hard to tell what's going on in the first 2 feet because it's a really dynamic system. Once we get past the first 2 feet, there's not a lot that can happen, right? Like, its kind of only option is to go down and end up in the groundwater. And so that's kind of how we first started visualizing some of our data. This is just an example of one of the anhydrous fields. These are all the sample dates in 2023 and 2024. And so we have that first 2 feet, kind of just the total. This is nitrate in pounds per acre. You can see it starts off pretty steady in the winter. That's kind of what we would expect. Like, there's not a lot happening in theory. Like, it should still be in its ammonia form. It shouldn't be doing anything. And then, like, it starts to ramp up as the soil ramps up, and then we can see it being used by the plant as well. And in addition to all of that happening, we are still seeing some of it in that lower, like 2 to 8 foot that we sampled as well. And so you can kind of see maybe the same-ish pattern, but like a tiny bit delayed. And so we slowly characterized, like the loss. Like, we know a lot of it's going up to plants too, right? But like, when we see the increases in that 2 to 8 foot zone, like, that had to have come from above, not below. And so we can see, like, that's some of it that's being lost to this kind of like transitional vadose. And as we see that start to leave, we can kind of start to pool up a fairly conservative estimate of how much nitrate is going to end up in the groundwater at some point. And we'll talk more about groundwater age dating and calculating when that point is. And so for this example, over a growing season, we're looking at 123 pounds per acre of nitrate that's eventually being lost. So not a perfect system, right? And then we also looked at same thing, but for ammonium instead of nitrate. And you can kind of see where it was applied in December, probably applied again in April based on, the numbers you see. And one of the things we found really interesting is we saw a lot more ammonium at depth than we anticipated. I think kind of common knowledge is ammonium has a positive charge. It's getting stuck, to the soil, and it's not moving. Well, we kind of saw that it is moving. And so some of the questions we had going into, this growing season that we're just finishing up right now are, is it moving? Like, is the ammonium itself moving, or is it nitrate moving and then getting converted back to, like, is it converting back and forth at depth? Like, what's happening there? Why is it doing this? Like, why do we have ammonium like running around in ways that we didn't think were happening? And like, why are they so high? And also, like, what's happening once that hits the water table, right? Like, is it going to stay ammonium? Is it going to go to nitrate? Like, it's like another potential source of stuff that we didn't consider as something that we needed to consider before. That makes sense. And so some of the preliminary observations from this first growing season, the early spring and summer precipitation might have been a limiting factor in that root growth. So we had a really shallow root ball. Our maximum movement of bromide was near 1 inch per day. So it's not as high as like some other places that have seen 1 foot a day of movement, but 1 inch a day can still get you pretty far in a growing season if you're thinking about nitrate and getting below 2 feet. So like all of that water, the shallow root zone, kind of leads to the likelihood, that the nitrate is getting past where the crop can use it. And once it's past where the crop can use it, eventually it's going to end up on our in our groundwater. So we're continuing to work with other experts like UNL, Ward Labs, agronomists to look at, like, what's the ammonium and where is that coming into things. And then, like I said, this grant is going to continue for the next 4 years, including Lower Loop, who, we started it with, and then Central Platte and Upper Big Blue. And so I think it'll be really interesting to see where things go next year in the growing season and looking at, like, where there are different soil types and different practices and things like that. And so now we're going to move out of our vadose zone and into our groundwater and talk about legacy nitrate. So we're still in that same area. We're looking at, the Lower Loop NRD and the Lower Platte North NRD and kind of where the two of them meet in that little juncture. Both of these NRDs have really high groundwater nitrate in those areas, which is, why we picked it as a study area. And And both of them are, they're working on their groundwater management plans and looking at, like, is our management plan effective? And like, how do we know based on what we're sampling? And so to determine this, we looked at groundwater age and nitrate concentration for 24 monitoring and domestic wells. And so kind of looking at the role of legacy nitrate on current groundwater quality and looking at some other things like denitrification, mixing, and things that might impact that water quality. And so I know I've said legacy nitrate a lot. And so sometimes there can be a big lag between when you apply that fertilizer on the surface and when it's showing up in your well, right? Like you apply something on the surface, your well is 300 feet deep at an inch a day. That's not going to get there in a year, right? Like, how do we know if we're only sampling our groundwater wells? Is that telling us what our management practices were like 2 years ago? Is it what are telling us what our practices were like 25 years ago? And so the idea of using the groundwater age is just to look at that effectiveness, right? So if we're having really high nitrate and our well is really old, it might not be reflective of what we're doing now. If we have really high nitrate and our well is 5 years old, not as great. And so that's just kind of the idea of, like this part of the project in legacy nitrate. And so we generally start counting groundwater age as soon as a water molecule hits the aquifer. So it's going to go through our vadosone. And then once it hits our aquifers times 0, it flows to a well, we sample it, and that length of time is like what we're considering our age. So the longer water is in the aquifer, the older it is. As you go deeper, because water flows both down and sideways, like with a regional or sometimes local flow path. And so the deeper you are, the older it tends to be. And things get a little weird at where it discharges into streams and things like that, and you have mixing. But in general, the deeper you are, the older it is. And so there are a number of different ways you can, I guess, sample for groundwater age, and it kind of depends on how old you think your groundwater is to start with. It's a little bit of a guessing game. And so carbon-14 is really common for older groundwater. We're talking 1,000 plus to 30,000 years. We don't care about that because there wasn't a lot of anhydrous ammonia going on 30,000 years ago. So we're looking at young groundwater, or what we're considering young groundwater, and young groundwater age tracers, so anything post-1950. And so when we're talking about things like that, we're talking about you used to be able to just use straight tritium, but we don't drop as many atomic bombs anymore, and so that's not as practical. So instead we look at tritium, helium, and that like decay and accumulation combined. And then we can also look at sulfur hexafluoride, which is a byproduct of things like electronics and also some sneakers. So it's accumulated really nicely in the atmosphere, and so it's a very nice young groundwater age tracer to use as well. And all right, you're gonna go. Okay, and so here, I know I should have mapped the wells earlier, but here's another map of the wells, monitoring and domestic wells. So we looked at both our helium, tritium, and our SF6 for groundwater age dating because things can go wrong in both of them. And we did actually end up with a geogenic source of SF6 in some of our samples, and so that threw everything way off, and so it was really nice to have the other set, our helium, tritium, to use instead. We also looked at nutrients, including nitrate, because obviously that was our focus. Major ions, trace elements, dissolved gases, stable isotopes, kind of, like the full suite of what you can sample for groundwater. And here we have our well depth and our nitrate. Half of our wells exceeded the EPA limit. We had a median that was over the EPA limit, and we had nitrate concentrations everywhere from below detection at 0.04 micrograms per liter to, or milligrams per liter, to almost 60 milligrams per liter. So we got a really nice range. There wasn't necessarily like a strong correlation with like if it was a domestic well versus a monitoring well, like there's a mix of everything. And we didn't really have a great correlation of nitrate in depth. So in general, like Bridger said, like as you get deeper, you tend to have less nitrate. We didn't necessarily see this here, but we also don't have like particularly deep wells, like if we're less than 200 feet, it's not like a super deep well. And so one of the things we looked at in addition to nitrate was denitrification. So this is a process in which nitrate becomes into gas. And once it's into gas, it's harmless to us. So like that's handy. We don't need to worry about it. And so what happens is if you have a source of nitrate and organic carbon and these delightful little microbes, the microbes will eat their way through dissolved oxygen because that's the easiest for them to eat. But once they've done that, they move on to nitrate because that's the next easiest for them to eat. So they'll eat their way through all of that and then they'll continue their way down the chain. But when we're looking at denitrification, you know, like that's the level that we're stopping at. And so by sampling for N2 gas, we can see if we have the excess N2 gas, we can back calculate what that would have been in nitrate. So 8 of our 24 samples had some indication of denitrification. And you can kind of see the sampled nitrate and then our back calculated what the initial nitrate is. And so for some wells, that's a fairly significant amount of nitrate being denitrified and like removed from the system. And then we have a couple other wells where the nitrate's pretty high and there might be some denitrification, but like the end result is still pretty high. And that might just be a function of time. The microbes haven't, you know, had a chance to eat their way down, or they might be getting enough nitrate continually inputting that like they can't eat down to compensate for the amount of inputs that they're getting. And so finally, to kind of tie it all together, we have our groundwater age and our nitrate. So as you can see from our lovely graph, our very high nitrate also happens to occur in our young wells. So not super great. So in general, the younger wells tend to be higher nitrate than the older wells. And all of our wells that exceeded that EPA MCL limit were less than 30 years old. And our 3 highest concentrations were like the 3 youngest wells. So the overall preliminary conclusions from this section of the projects. So half of them exceeded the MCL. There was some denitrification, but it wasn't, you know, like a predominant thing that was ongoing in this area. In general, the youngest wells tended to have the highest nitrate, and so that kind of indicates that current management strategies aren't as effective as they could be, right? Like we're not talking about a legacy nitrate in this situation. We're talking about a more current strategy. And so kind of combining these 2 projects together, they're kind of telling the same story, right? We are still seeing nitrogen losses past the root zone under, and I will say it wasn't just the anhydrous. We saw, I have extra charts if you guys really want to look at them afterwards. We saw nitrate losses in all 3 fertilizer practices. So like we are still seeing, like, based on current management strategies, it's not a perfect system. There is still nitrate loss. And there is, you know, like we are seeing that show up in the groundwater. And so as part of this, and I think this has been mentioned before, there's now a governor's task force to look at water quality and water management. And so Chris, the other person who couldn't be here today, went and talked about that a few weeks ago, kind of sharing our soil nitrate results from the first season. And it was really interesting to see, you know, like the different NRDs come together and talk, and like specifically talking about like practices and having producers and other people there. He said it was really interesting to see that, you know, like some of the NRDs are like, you guys are still doing fall fertilizer? Like, we got rid of that like years ago. You know, like it was different parts of the state have, you know, different management practices. And so it seems like this task force has been a good way to maybe share results and share practices that maybe haven't been talked about in the same way before. So this is just the boilerplate